Hello everyone, and welcome to today's chem lesson. Today we are going to look at our second of three trends, electronegativity, and how we can use the four corners of the periodic table, the number of shells, the number of valence electrons that these elements have, to determine which has the highest electronegativity, which has the lowest electronegativity, and which direction our trend is going to go. Electronegativity is different. Right? Ionization energy is all about how much energy it takes to remove an electron. Electronegativity is a measure of how good an element is at getting new electrons. Right? If we're talking about electrons as something you hold on to, ionization energy is how good are you at holding on to your electrons? And electronegativity is how good are you at taking electrons from others. Electronegativity is measured on a scale from 0 to 4, with 4 being the highest, but there is no actual measurement, there's no unit for electronegativity, it's just a comparative scale. It's like saying on a scale from 1 to 10, how much do you enjoy chocolate? Right? You don't say like 10 happy faces worth of chocolate. Right? It's just a scale from 1 to 10. This is a scale from 0 to 4. It's a comparative scale. Our elements that have a lot of valence electrons, our elements with 6 and 7 and 5 valence electrons, are going to have high electronegativity. They want to gain electrons. They are going to be good at taking electrons from other things. On the other hand, elements with 1 or 2 or 3 electrons are going to be bad at taking new ones because they don't even want the ones they have. They want to lose electrons. So they're going to have a low electronegativity, while elements that want to gain electrons are going to have a higher electronegativity. And we're going to take a look at our four corners again and see what we can see and see what trends we can figure out about electronegativity. Right, our four corners are lithium, fluorine, francium, and ununceptium, which doesn't start with an F. Lithium has 2 shells and 1 valence electron. Fluorine has 2 shells and 7 valence electrons. Francium has 7 shells and 1 valence electron. Ununceptium has 7 shells and 7 valence electrons. And now we want to figure out which of these elements are really good at getting new electrons and which ones of these are bad at getting new electrons. How strongly can these elements pull on new electrons? We said a minute ago that elements with high numbers of valence electrons are going to be good at gaining new electrons. These two up here with 7 valence electrons are going to have a high electronegativity. Right, they're better at attracting electrons because they're so close to finishing their set. They want to get up to 8. They are going to try really hard to pull in new electrons. On the other hand, though, lithium and francium, they've got 1 valence electron each. They don't want to pull in more, they want to lose the one they have. So they are going to have low electronegativity. They are not trying to get new electrons. So that makes our, horizontal trend a lot easier to see. As we move from left to right, electronegativity increases. And now the reasoning here is because the more valence electrons an element has, the stronger they're going to try to pull on more electrons. As we get closer to 8 valence electrons, that I say they want to, or they that's what they want, that's what they desire, but they're elements. They don't actually have wants and desires, but they're going to be more stable if they pull in those new valence electrons to finish up their shells, right? To get up to 8, that magic number of 8. Now, that's not the only direction we want to look at the table in, though. We want to look at it from left to right, but also up and down the column. So when we take a look between lithium and francium, or ununceptium and fluorine, we see two elements that want to gain electrons. But we know that one of them must be better at gaining than the other because they're different elements. Which one of these do you think is better at gaining electrons? They both have 7 valence electrons. They both want to gain more electrons. But if we're looking here at which one is going to be better at it, fluorine is actually going to be the better element at gaining electrons. So as we go up the table here, with preferably straight lines to make an arrow, or just whatever this became. As we go up the table, we get better at gaining electrons. Our electronegativity is going to increase the closer you are to the first and second row. And the reason here is because of the number of shells. Ununceptium is holding on to 6 shells worth of electrons, and also these 7 electrons here. And so if it's trying to juggle all of these electrons and also add another one in, it's going to be more difficult than fluorine, which has 1 shell and 7 valence electrons to juggle. And so electronegativity increases as you go up the table, because fewer shells means that the element is less encumbered, makes it easier to pull in electrons. And the same thing holds true here for francium and lithium. Right, lithium has a higher electronegativity than francium does. They are both low, but lithium has fewer shells, so if it did gain electrons, we would see lithium having an easier time doing that than francium. And actually, while we're on that topic, we've got 4 electronegativity values. Can you correctly assign them to our 4 elements here? Think about what we just talked about and see if you can assign these 4 electronegativity values correctly to the elements. Good, 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 good. So let's take a look at this. All right, I'm seeing correct answers pop up here in the chat. Right. We've got 2 low values and 2 high values. 2 of these elements want to gain electrons and 2 of them want to lose electrons. We're going to put the 3 and the 4 over here on the right side of the table, because these 2 elements want to gain electrons. They're going to actively seek out electrons to grab, so they're going to be good at it. While lithium and francium, they want to lose electrons, and so they're not going to be looking for electrons to take. Now, between lithium and francium has 7 shells and 1 valence electron. So it has a lot of electrons to juggle. Right, a lot of electrons to juggle, but also it doesn't want to gain any new ones. So it is going to be the worst at getting new electrons. Lithium, still very bad at gaining electrons, is going to be better than francium. We're going to give the second lowest value. Over here, unseptium has more shells than fluorine does, which makes it a little bit worse at gaining, even though they both want to gain. Right, perfect. Fewer shells attract more electrons, right? Fewer shells means it's easier to pull in those electrons. Even if you don't want them, right? Like lithium here, even if you don't want them, it's easier for lithium to pull in electrons than it is for francium. And when we take a look, when we zoom out from our 4 corner elements and look at the periodic table as a whole, we see that electronegativity has the same trend as ionization energy. The closer you get to the upper right, the higher that value is. The closer you are to the lower left, the lower that value is. And just like before, if we take any 2 elements on the table, you should be able to tell, just by looking at their placement, which one is the higher electronegativity. And in this case, we see X is higher than Y. They're both in the same column. X is going to have the higher electronegativity. If we do these two over here, we're going to know that B has the higher electronegativity. It's higher up on the table and also further right. It doesn't matter what these two elements are. We can tell their electronegativities, their comparative electronegativities, just based on placement on the table. Electronegativity is going to come back in a pretty big way as we move forward and start to talk about bonding and the way that elements interact with each other. And something with a high electronegativity is going to be really good at pulling electrons and either taking them away from an element or just being more in charge of the electrons that they share. But for now, we're going to transition over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.